Can we have my slides? Ah, yes. Thank you. So, yeah, as Norbert already said, my talk is about aspect-based similarity of research papers. And to understand that, let's go back to how classical document similarity, this is not really working. Ah, okay, thank you. How classical document similarity is used in information retrieval applications like recommender systems. So usually you have one seed document, and then you generate the recommendations based on how similar the seed document is to candidate documents. But this has kind of a problem, right? Because when you have, for instance, research papers, right? Research papers can be similar in many different ways. And that's why aspect-based similarity is there. So this means that you want to generate recommendations or measure the similarity always dependent on the aspect you're considering. And this means that the similarity can change depending on the aspect. And in related work, what's usually done is, for example, segment level similarity. This means that you divide a document into segments based on the aspects the segment is about, and then you compute the similarity based on these segments. But this requires, of course, breaking up documents, and is therefore not really optimal. Another approach is the pairwise document classification approach, where you have a classifier and apply the classifier on pairs of documents. And then you have a multi-class classification scenario. But this requires to classify all possible pairs in your document corpus, which of course is then not really scalable. If you're working with like a normal corpus that you can find in a digital library. And that's why we were thinking about how we could improve this. And we're now focusing on aspect-specific embeddings. And to understand this, let's first talk about kind of classical document embeddings. This means that you usually have one embedding function that maps your document to one document vector, right? But what we are doing instead is that we have the embedding function combined with the aspect that we are interested in, which then maps, depending on the aspect and the document, the documents into aspect-specific embedding spaces. So for each aspect, you would have one embedding space. And in order to do this, we need data. So we are in a supervised learning setting. And for that, we need to define our set of aspects. So it's predefined. And we need aspect information given in the form of triples, like a document A, document B, and a label that says if document A and B are similar or not in this particular aspect. And we found this with Papers with Code. For those who don't know Papers with Code, that's a website where you have a hand-curated collection of mostly machine learning papers. And at the time of writing, they had around 150,000 papers. By now, it should be much more. And in addition to them linking papers with their code repositories, they also associate papers with the task the paper is about, and the method that is applied, and the data set. So here we have then these three aspects: the task, the method, and the data set. And based on this, we construct our data set for our experiments. And just to give an example, we have, for instance, a task like speaker recognition or object detection, methods like LSTM or transformer. And here on the left, you can see the kind of distribution And what you can see here is that we have an unbalanced data set. So we have most papers for the task aspect and least papers for the dataset aspect. And based on this data, we then evaluate our methods that we test here. And we have a set of baselines, which are generic document embeddings. So just like the traditional document embeddings, where you have one embedding for each document without any aspect information. There we have fast text word embeddings. We have the transformer Cybird, and we have Spectre, which is a variation of Cybird, but trained with a contrastive loss on citation prediction. And we also have one pairwise classification approach with Spectre, but we just use this in a kind of restricted fashion because it's not really scalable even to the relatively small corpus that we are using. And we compare these methods to specialized embeddings. So here we have our specialized embedding function where you put in the document, the aspect, and you see you get the aspect specific embeddings. And there we have one retrofitting method combined with the generic embeddings from before. Retrofitting means that you have you put in the generic document embeddings and then map them to the aspect-specific embedding space. Also, we have fine-tuned transformer variations and CMEs transformers. And all of these methods are used in a k-nearest neighbor search setting. So we take a seed document, then retrieve with these methods the candidate documents, and then measure if a candidate document has the same task, the same method, or the same data set, and then say it's a relevant recommendation. Okay, let's look into the results. So here on the left, you see the methods, and in the center, you see the map at 10, the MRR at 10, for task, method, and dataset separately. And what we see here is that by a large margin, the CME Cybird outperforms all other methods. And just maybe as a side note, so maybe you're wondering why we have CME Cybird but not CME Spectre. At the time of writing, we had some problems with the implementation, which we fixed by now, and we rerun the experiments. And I can say that the difference between CME Cybird and CME Spectre is not really significant, so you can assume that the results are comparable. The second best method is the pairwise Spectre approach. But this is something what you need to know here is that this method is by far the most compute intensive method. And even though it's just kind of the second best method. Among the generic embeddings, we see that Spectre is the best. And what we also can see here is the comparison to Cybird. Cybird has very poor results. And this is aligned with related work that shows that if you want to do similarity search, you should not just take the embeddings directly from a transformer model, because the embedding space is poorly defined in some areas, and that's why the similarity search doesn't work that well. For retrofitting, we have a mixed effect. So for fast text, retrofitting improves the results, and for Spectre, it decreases the results. And this is, I think, due to the fact that the retrofitting method was originally developed for word embeddings, so it's not really suitable for transformer models. And what we also see is here the fine-tuned transformer is also not really working, and we attribute this to the fact that in the fine-tuned transformer, we jointly encode two documents, and this is different to the actual task, kind of when we want to encode each document separately. And that's why we have this poor results here. But more interesting are the aspect results if you compare them. And this is what we see here, is that generally for method, we have kind of low results. The highest results we generally see for the task aspect, which of course can somewhat be explained to the unbalanced data set, but not completely. And this also follows if we look how the performance changes as we specialize the embeddings. And what we see here is that the performance gap between the aspects, so from method or to dataset, for example, decreases from Spectre embeddings to the semi-cyberd embedding. And kind of having these aspect performance difference raises the question whether there's like a systematic difference between the recommendations generated from generic embeddings and aspect-specific embeddings. That's why we looked into the overlapping recommendation sets. And this is what you can see here is that if you compare generic embeddings like FastTech and Spectre with each other, you have a relatively high overlap. But if you have the aspect-specific embeddings, you see, more interestingly, that you have very few overlapping recommendations in the method aspect, but more, or kind of the most overlap in the dataset aspect. And this was also kind of confirmed by our qualitative evaluation. And this indicates that you have an implicit bias in the generic embeddings towards the dataset aspect and against the method aspect, which raises an interesting question, right? Do we really want to have this in a recommender system? Do the users also want to have more dataset-oriented recommendations? And of course, here we would attribute kind of this difference not really to the methods themselves, but rather to the corpus that you are using. So you can imagine that kind of research papers more often list the data set name in the title or in the abstract compared to like a detailed method. Okay, so let's conclude. We shown that the best generic method, Spectre, was pretty much outperformed by the best specialized method, which is not really a surprise, right? Because generic embeddings were used in a kind of zero-shot fashion. We didn't train them for specific aspects, which of course also means that kind of for the aspect specialized embeddings, we used labeled data, right? And this is of course currently still one big weakness, right? That we need data, and we are in a supervised setting. But I'm quite confident that with projects like the Open Research Knowledge Graph, more and more of such data will be available. And for the reason why we have the CMEs cyberd as best methods, as I said, kind of the retrofitting method was originally developed for word embeddings. That's why it doesn't work that well. And compared to the vanilla fine-tuning of transformers, the CMEs version independently encodes documents. So, and in contrast to the fine-tuning, where you have this pairwise classification, and this is in the end also, or is more similar to the task that we're doing in the end. And lastly, what we've shown is that by kind of transferring this aspect-based similarity problem into a just like classical similarity search problem in aspect-specific embedding spaces, we can achieve a scalable recommender system. And this is also how I want to end my talk. We built a demo, so you can go to Hugging Face Spaces and try our embeddings with your own papers. So you get your recommendations for method, data set, or task, depending on your paper. So yeah, thank you very much. And I'm happy to answer your questions.